Hello everyone. In a previous lecture, we have studied what is meant by the compressible flow and then the basic functions of the compressible flow. In this lecture, we are going to study the velocity of the sound or pressure wave in a fluid. As we know that the disturbance in any medium is transmitted from one point to the other. The medium may be a solid, liquid, or the gaseous, and thus the disturbance is traveling with some velocity, and this velocity is depends upon the distance between the molecules. Okay, the velocity of the disturbance is depends upon the distance between the molecules. If we consider the solids, then the molecules are closely packed and hence the disturbance is transmitted instantly. Because of the molecules are closely packed, the disturbance is transmitted quickly or instantly. But if we consider the liquids or the gases, the molecules are not closely packed. There is some distance between so the disturbance will be transmitted from one molecule to the next molecule. And if we consider the fluids, there is some distance between the adjacent molecules. So the molecules are not closely packed. There is some distance between the adjacent molecules. So the each molecule will have to travel certain distance before it can transmit the disturbance. Okay, so each molecules are apart from each other. Okay, and there is some distance between each molecule as in the case of the fluid. So the each molecule have to travel certain distance before it can transmit the disturbance. Okay, and hence the velocity of the disturbance in the case of the fluid is less than the velocity of disturbance in the solids. Okay, velocity is depends upon the distance between the molecules. This distance is smaller in the case of the solids and it is bigger or larger in the case of the fluid. So the velocity of the disturbance is less as in the case of the fluids, whereas the velocity of the disturbance is more in the case of the solids. The distance between the molecules is related to the density, which is depends upon the pressure as in the case of the fluids. Here, the distance between the each molecule depends upon the density. Okay, and density depends upon the pressure as in the case of the fluid. So the velocity of the disturbance is depends upon both the change in the velocity and also change in the density of the fluid. Okay, then now we will solve the expression for the velocity of the sound wave in a fluid. For this, consider a horizontal pipe. Here in the figure you can see the horizontal pipe is there. Okay, and on the left side of it horizontal pipe a piston is provided. Okay, and this piston is creating the disturbance. The disturbance is created the pressure, and due to this disturbance the pressure waves are created. These pressure waves travel with the velocity of sound in all directions. Okay, and so here we are considering the one dimensional flow. Okay, this pipe is horizontal. Okay, and one side of it is distance provided. Okay, and then here in this pipe is completely filled with the compressible fluid. Okay, then the pipe is having an uniform cross-sectional area. Okay, the piston is moved towards the right. As here in the figure you can see the piston is provided on the left side of this horizontal pipe, and this piston is moved towards the right. Okay, the dotted line showing the displacement. Okay, and due to this displacement the disturbance are created in the fluid, and this disturbance is in the form of the pressure waves which travel in the fluid with the velocity of the sound waves. In the figure you can see here is a piston, and this piston is moved from here to here, means it is covering the distance x, okay, at the time dt, okay, and due to this uh, um, movement of this piston, the disturbance is created and the pressure waves are generated, and this pressure waves is traveling a distance, mm, uh, traveling traveling a distance L. Okay, here the L indicating the distance traveled by the velocity of the sound wave. Okay, so let A is the here. Let A is the area of the cross section of the pipe. V means the velocity of the piston. P indicating the pressure of the fluid in a pipe before the movement of the piston. Okay, and density rho is equal to density of the fluid before the movement of the piston, and dt is the a small time interval of the time which the piston is moved. C indicating the velocity of the pressure wave or sound wave traveling in a fluid. Now we have to calculate the distance traveled by the piston in a time dt, which is equals to velocity of the piston into dt, which is equal to v dt. Okay, in the figure you can see here a distance traveled by the piston in a time dt, means the distance is moved from here to here. It is covering a distance x. Okay, so the distance x is equal to the velocity of that piston into the time. So x is equals to v into dt. Okay, this is the distance traveled by the piston in the time dt. Now we will calculate the distance traveled by the pressure wave in a time dt. Okay, during the piston movement of the piston, the pressure waves are generated and it is traveling a distance from here to here. Okay, the distance traveled by the pressure waves are from here to here. So we have to calculate the distance traveled by the pressure wave in a time dt, which is also equals to velocity of that pressure wave into dt. The velocity of pressure wave is indicated by c. Okay, so pressure wave velocity of pressure wave is c into the distance dt. So the distance traveled by the pressure wave in the time dt is equal to c into dt here, which is indicated by the capital L. Distance traveled by the pressure wave in the time dt is equals to, means L is equals to c into dt. Okay, this the value of the c is very large. The value of the c, that is the velocity of the pressure wave, is very, the value of this pressure wave is very large. Therefore the value of c into dt is more than the v into dt. The value of c dt is more than the v dt. For the time interval dt, the pressure wave has traveled a distance L. Here the pressure waves has traveling a distance L, whereas this piston moved through the x. Okay, at the time dt, the velocity, the pressure waves is traveling a distance L and the piston is traveling a distance x. Okay, thus the length of the tube equals to L minus x. The fluid will be compressed. Okay, here this is the L and this is x, and in this L minus x, this portion over here, the fluid will be compressed, and due to this compression of the fluid, the pressure and density of the fluid will be changed. Due to this compression, the pressure and the density of the fluid is changed. So the change in the pressure is equals to, means P is the pressure before compression, then the after compression the pressure will become P plus dP. Okay, so let P plus dP is equals to pressure after the compression. Also, with this pressure, density also changes. So density before compression is indicated by rho, and after the compression it will become rho plus d rho. Okay, so let rho plus d rho is equals to density after the compression. Now the mass of the fluid for the length before compression. Here we have to calculate the mass of the fluid for this length L before the compression. Means here without before compression, okay, the mass of the fluid is equals to density of that fluid into the volume of that fluid. Okay, so density and into volume means what? Area into length. So it will become rho into A into L. Okay, but as we know that L is equal to C dt. So put here over here. Then the mass of the fluid for the length before compression will become rho A into C dt. This is our first equation. Okay, so here we are finding out the mass of the fluid before compression. Then we will calculate the mass of the fluid after compression. Means after the compression the piston is moved from here to here. Okay, so remaining portion is over here. Means the length will becomes L minus X. Okay, so the mass of the fluid after compression for this length L minus X will become density after the compression into the area of the length. Density after compression we are considering as P plus dP. Density rho plus d rho into the area into the length means L minus X. Okay, so here P plus dP into A. As we know that L is equal to C dt and X is equal to V dt. So equation becomes P plus rho plus d rho in bracket complete into area into in bracket C dt minus V dt. This is our second equation. So up to here we have calculated the mass of the fluid before compression and the mass of the fluid after the compression. Okay, then we know that the continuity equation. From the continuity equation, the mass of the fluid before compression must be equal to mass of the fluid after the compression. Means equation 1 is equals to equation 2. Write down over here rho A C dt. Here rho A C dt must be equals to P plus rho plus d rho bracket complete into area into C in bracket C dt minus V dt. Here dt and dt is cancel out. Okay, so it will become P rho plus d rho into area into, so here dt and dt is common. Okay, so it is taken outside. So the equation becomes rho plus d rho into area into dt in bracket C minus V. Okay, so here ADT and ADT is on both sides, so we can divide these both terms by A into dt. Then after dividing this term by ADT we will get rho into C is equals to P rho plus d rho bracket complete into C minus V bracket complete. Okay, so it must be equal to dividing this term rho into C minus rho into V plus C into d rho minus V into d rho. Okay, so we will get C into d rho is equals to rho C minus rho C plus PV plus V into d rho. So it must be equals to rho V plus V d rho. Okay, so this is our third equation. But the velocity of the pistons means capital V is very small as compared to the velocity of the pressure wave C, means V is very less than the C. So here also the density also very small. This term is very small. V into dp is, this term is very small. So here it is neglected. Now the equation 3 becomes C into d rho is equals to rho into V. This is our fourth equation. Okay. Now the piston is moved with the velocity v in the time dt, which the fluid with which is at the rest initially will move with the velocity equals to the velocity of the piston. Then the if we apply in the impulse momentum equation, then it will become net force on the fluid must be equals to rate of, formula for the impulse momentum equation is net force on the fluid is equals to rate of change of momentum. Net force on the fluid is equal to what? Pressure before compression, sorry, after compression into area minus pressure into before compression into area is equals to rate of change of momentum means what? Mass per second into change in the velocity of the fluid. Here p plus dp into a minus p into a. Okay, so if we multiplying this term, we will get p into a plus dp into a minus pa. So pa are cancel out, the remaining terms is dp into a. So here we get dp into a is equals to is equals to mass per second, means total mass per second means time into change in velocity capital V minus 0. Okay, so we will get total mass means what? Rho A upon time. Here is we are considering dt. Then velocity, change in velocity means V minus 0. Okay, final velocity minus initial velocity is 0, final is V. Okay, then we will get as we know that L is equal to C dt, put this value into the equation, we will get rho into A, instead of L we are adding C dt upon dt into V minus 0. So dt are cancel out, the remaining terms are rho AC in bracket V minus 0. So we will return as rho AC into V. Okay, so dp into a is equal to rho a c into v. Then if we a is taken on the right side, we will get dp is equal to rho a c v upon a. Okay, the a are cancel out, so dp is equals to rho c into v. Then c is equals to what? dp upon rho v. This is our fifth equation. Okay, so here we are getting the value of c as dp upon rho v. This is our fourth equation. Already we have calculated the value of c as c into dp is equal to rho v. So multiply this fourth equation and fifth equation. Multiplying equation fourth and fifth, we will get c square dp is equals to rho v into dp upon rho v. Okay, so rho v are cancel out. C square dp is equal to c square d rho is equals to dp. Then c square is equal to dp upon d rho. So c will become under root of dp upon d rho. So this is our equation, final equation for the velocity of the sound. Okay, so this equation gives the velocity of the sound, which is the square root of the ratio of change in the pressure to the change in the density of the fluid due to the disturbance. So velocity of the sound is equals to integration of is equals to under root of ratio of change in the pressure upon change in the density. Okay. uh, Now we will calculate this velocity of the sound in terms of the bulk modulus. The bulk modulus is indicated by K, and it is defined as increase in pressure upon decrease in volume upon original volume. Okay, so K must be equals to dP upon decrease in volume is upon original volume, means minus dV upon V. This is our sixth equation. dV showing the decrease in the volume and V is the original volume. So negative here this symbol we are called it as for all. Okay, so or we can see V. We can call it as V also. Original volume and decrease in volume. So negative sign is showing that with the increase in the pressure the volume decreases. Okay. Now we know that the mass of the fluid is constant. Mass means what? Rho into volume. Density into volume means what? Mass. So if mass is constant, then density into volume also constant. That is rho into V is equals to constant. Okay. Now differentiating this term, we will get first term differentiation of second plus second term differentiation of first is equals to 0, means P into dV plus V into d rho is equals to 0. P into dV is equals to minus V dP. Then we will get minus dV upon V is equal to d rho upon rho. Okay, so here in the equation we will get the value of this term as d rho upon rho. So put over here in the equation 6. Then K will become dP upon d rho upon rho, which is equals to rho into dP upon d rho. So dP upon d rho is equals to K upon rho. Okay, but we know that C is equals to under root of dP upon d rho. We have solved the expression for the velocity of the sound wave, and we get the value of C as under root of Cp under root of dP upon d rho. Okay, but here dP upon d rho is equal to K upon rho. So C must is equals to under root of K upon P. This is our next equation. So this equation gives the velocity of the sound wave in terms of the bulk modulus and the density. Okay, this equation is applicable for the liquids and the gaseous. Then we will calculate the velocity of the sound for the isothermal process and also for the adiabatic process. For the isothermal process, we know that the relation between the density and the pressure is P upon rho is equals to constant. Okay, so P into density raised to minus 1 is equals to constant. Then differentiating this term, we will get P into minus 1 rho raised to minus 2 dP d rho plus rho raised to minus 1 dP is equals to 0. Dividing this whole term by rho raised to minus 1, then we will get rho minus minus P rho raised to minus 1 d rho plus dP is equals to 0. Okay, so it is also equals to minus dP upon rho d rho plus dP is equals to 0. Then we will get dP is equals to P upon rho into dP. So dP upon d rho is equal to P upon rho. But we know that from the equation of this state, we know that P upon rho is equals to RT. So put over here dP upon d rho is equal to P upon rho, which is equals to RT. So indirectly dP upon d rho is equals to RT. So The equation of the velocity of the sound for the isothermal process will become C is equals to, as we know that C is equals to under root of dp upon d rho. Instead of dp upon d rho, we are putting p upon rho, which is also equals to under root of rt. So this is the equation for the velocity of the sound for the isothermal process. Okay, now we are calculating the velocity of the sound for the adiabatic process also. Adiabatic process, the relation for the adiabatic process, we know that the relation between the density and the pressure P upon density raised to K is equals to constant. So we can also can be written as P into density raised to minus K is equals to constant. Okay, now differentiate this term. After the differentiation, we will get P into minus K into density raised to minus K minus 1 into D into rho plus P rho raised to minus K into dP is equals to 0. This is the integration of this term. Okay, and this term. Now divide this whole term by density raised to minus K. Then we will get minus P K density raised to minus 1 d rho plus dP is equals to 0, which can also be written as dP is equals to P into K upon rho into d rho. Okay, so dP upon d rho is equals to P upon rho into K, but we know that the equation of the state P upon rho is equals to RT. So put over here RT into K. So dP upon d rho will become K RT. Okay, so if we put as we know that the velocity of the sound is equals to under root of dP upon d rho, which is equals to under root of KRT. Okay, so this is the velocity of the sound for the adiabatic process. Okay, so up to this we have calculated the velocity of the sound, formula for the velocity of the sound. Okay, then the velocity of the sound in terms of the bulk modulus. Then we are finding the velocity of the sound for the isothermal process and for the adiabatic process. Okay, then our next point is the Mach number. As we know that Mach number is defined as the square root of the ratio of the inertia force of the flowing fluid to the elastic force. Here the Mach number is equals to under root of inertia force upon the elastic force. Inertia force means what? Rho into a square. Elastic force is K into A. Okay, so here under root of rho a v square upon K into A. So here A is common in the denominator and numerator, so it is cancelled out. Then it will become remaining terms are under root of v square upon K upon rho. Okay, so here v is equals to v upon under root of K upon rho. As we know that under root of K upon rho is equals to C. Okay, so put over here, then Mach number will become V upon C. Okay, V means what? The velocity of the sound or the body moving in the fluid. Okay, upon C means the velocity of the sound in a fluid. Then Mach number will become V upon C. Okay, the formula for the Mach number is V upon C. Then for the compressible fluid flow, the Mach number is an important non-dimensional parameter because On this Mach number, the fluid is divided into three categories: supersonic flow, sonic flow, and subsonic flow, supersonic flow, and the sonic flow. Okay. So here first is the subsonic flow. Subsonic flow means what? A flow is said to be a subsonic if the Mach number is less than 1. Okay, so the value of the Mach number when is less than 1, then the flow is said to be an subsonic flow, or the velocity of the flow is less than the velocity of the sound wave, then that time we can call it as an subsonic flow. Then the second law is the sonic flow. Sonic flow means when the Mach number is equals to 1, then the flow is said to be a sonic flow, or when the velocity of the flow is equals to the velocity of the sound, v is equals to c, then that time the flow is said to be a sonic flow. Okay, and the third law is the supersonic flow. The flow is said to be a supersonic flow if the Mach number is greater than 1. Okay, means capital M is greater than 1. That means when the velocity of the flow means capital V is greater than the velocity of the sound wave, then the flow is said to be a supersonic flow. V is greater than C, then the flow is said to be a supersonic flow. Okay, hope you understand all this concept well. Now we will solve the problems on these topics, means the velocity of the sound waves and also on the Mach number. So first problem is find the sonic velocity for the uh, following fluids. The crude oil of specific gravity is 0.8 and the bulk modulus as 153036 Newton per centimeter cube. And second is mercury having a bulk modulus of this. So, okay, so first case we are considering, okay, and finding out the sonic velocity. Here they have given that the bulk modulus they have given. Okay, so uh, and they have given the specific gravity of the crude oil. Specific gravity of the crude oil is 0.8. From that we can calculate the density. Density of that crude oil is equals to 0.8 into 1000, so it will becomes 800 kilogram per meter cube. Then bulk modulus they have given in the example is 153036 Newton per centimeter square. Convert it into the Newton per meter square. As we know that for the sonic for the relation in terms of the Mach modulus uh, for calculating the velocity of the sound is c is equals to under root of k upon rho. The value of k is under root of 153036 into 10 raised to 4 upon 800. So we are getting the value of c as 1383 meter per second. Okay, so here case 1 is solution for the case 1 is we are getting the value of c as 1383 meter per second. Now case 2 is considering. Okay, for the case 2, the mercury is having the bulk modulus of, and they have given the bulk modulus as 2648700 Newton per centimeter square. Okay, they have given that the mercury, okay, we know that the specific gravity of the mercury is 13.6. Density of the mercury will become then 13.6 into 1000 kilogram per meter cube. Okay, now the sonic velocity is equal to under root of k upon rho. So after putting the value, we get the value of c as 1395.55 meter per second. Okay, so case 2 is also solved. Okay, now we will see one more problem. Here, find the speed of a sound wave in air at a sea level where the pressure and the temperature are 10.1043 Newton per centimeter cube. That is, here they have given here the absolute temperature. Then and the 15 degrees centigrade. Absolute pressure they have given, and the temperature is 15 degrees centigrade, and the value of R is 287 joule kilogram degree Kelvin, and K value is 1.4. Okay, so here they have given the value of pressure as 10.1043 Newton per centimeter square. Convert it into the meter, that is equals to 10.1043 into 10 raised to 4 Newton per meter square. Then they have given the temperature is equals to 15 degrees centigrade. But here the temperature is not absolute, so we have to calculate the temperature, absolute temperature. So capital T is equal to 273 plus 15 degrees, so it is equals to 288 degree Kelvin. Okay, then value of R as 287 joule kilogram degree kg degree Kelvin plus degree Kelvin, and K is equals to 1.4. As we know that for the adiabatic process, the velocity of the sound is given by the equation C is equals to under root of KRT. Put the value of KRT. Value of K is 1.4, R is 287, and T is 288. Then after finding out solving this, we get the value of C as 340.17 meter per second. Okay, then now we will see one more problem. Calculate the Mach number at the point on a jet propelled aircraft which is flying at 1100 kilogram per hour at sea level where air temperature is 20 degrees centigrade. Take K is equals to 1.4 and R is equal to 287. So here we have to calculate the Mach number. As we know that the value of Mach number is, formula for the Mach number is V upon C. So V means what? The velocity of the sound velocity they have given of that velocity of that jet propelled aircraft, they have given as 1100 kilogram per hour. So speed of the aircraft means V is equals to 1100 kilogram per hour. So convert it into the meter per second. For that it will the relation is, the equation is 1100 into 1000 upon 60 into 60. We will get the value of speed of the aircraft in the meter per second, which is equal to 305.55 meter per second. Then the temperature they have given as 20 degree. Then the absolute temperature will become 273 plus 20, which is equals to 293 degree Kelvin. Then the value of K they have given as 1.4 and R as 287 joule kg degree Kelvin per. Okay, then as we know that the velocity of the sound, the equation is under root of KRT. Then we will get the value of C as 343.11 meter per second. Okay, now the Mach number is equals to V upon C. Value of V is 305.55 and C is, we have calculated the value of C as 343.11. So value of M, that is Mach number, is equals to 0.89. So here we get the solution of that problem. So our next problem is, an aeroplane is flying at an height of 15 kilometer, where the temperature is minus 15 degrees centigrade. The speed of that plane is corresponding to m is equals to 2. Assuming that k is equals to 1.4, r is equal to 287, find the speed of the plane. So here they have given the height of that plane, temperature they have given, then the Mach number, the value of k and r they have given, and we have to calculate the speed of that plane. So here z, that is the height of that plane, they have given z as 15 kilometer, but this is an extra data, we are not required this value into for solving the problem. Okay, so this is an extra data they have given in the example. Temperature they have given as minus 15 degrees centigrade, then the absolute temperature is equals to minus 50 plus 287, which is equals to 223 degree Kelvin. Mach number is 2, k is 1.4, r is 287. Then the velocity of the sound, c is equals to under root of krt, under root of 1.4 into 287 into t is 223. So we get the value of c as 299.33 meter per second. Okay, then Mach number they have given, m is equals to v upon c. Mach number is 2, we don't know, we have to calculate the value of v, and c we have calculated as 299.33. so v is equals to 2 into 299.33, which is equals to 598.66 meter per second. Here is the answer. Here we get the speed of that plane. Okay, then if we have to calculate this speed into the kilometer per hour, then v is equals to 598.66 into 60 into 60 upon 1000, so it will becomes 2155.17 kilometer per hour. Okay, so here the value of v, that is the speed of the plane, is 2155.17 kilometer per hour. Okay, so in our problem is solved over here. In this lecture we have studied the velocity of the sound, then the velocity of the sound in terms of the bulk modulus for the adiabatic process, for the isothermal process. Then we have studied the Mach number. Okay, and then the class on the basis of the Mach number, the types of the fluids, types of the flow. Okay, and then we have solved the problems on the same. Okay, thank you.